Hello everyone, this is Peeps, and today I'm going to be playing some Hydroneer, doing a logic build in my creative test world where I want to solve a problem. So we'll start off. Oh, it's a beautiful day in the ocean. I'm at South Hope. This is where I do a lot of my logic testing, and the problem that I want to solve is going to be right here. So this is a very common issue that people run into. Your filter is broken. Your hopper is out. So when the filter is broken, your detector is going to look at the durability and see that it's at 0. It's going to output a 0. You have a flip hook that's going to output 1 in place of the 0. And then your hopper, when it receives a 1, is going to send out whatever wrench it's got. So if you have anything other than a 0 being sent out, your flip hook sends a 0, so your hopper doesn't do anything. But if your hopper runs out, the only way that you know is to go over here and check for yourself. So what ends up happening is your entire system can shut down if you aren't keeping up with your hoppers. And I want to create a way of being able to identify when my hopper is about to go out without just going and checking on it myself. And in the builds that I do, I have a few different areas where I use filters and hoppers to be able to get things set up. So if we look over here, I've got a hopper that's set up and it's got some wrenches in it. Over here I've got a weight detector pointed at it, and over here I've got a durability reader pointed at it. And if I were to flip it and we watch a wrench fly out of it, flew out, the number's gone down, but neither the weight reader nor the durability detector have actually triggered anything. So there's not a way very easily to identify other than my eyeballs going over here to see that we have in fact launched a wrench. So essentially what we're going to have to do is we're going to have to count how many times that hopper has actually sent a value. So to do this, we have a binary clock, and this is what we're going to be building today, is a binary clock that we can program to send a signal at a specific time. Now luckily for us, the hoppers aren't being triggered constantly. They are actually very slow because they don't get, the durability goes down slowly. So because we have a few seconds delay within our circuit systems that I'm going to be showing you in a little bit here, the timing doesn't have to be as fast as possible, which is good. Logic is unfortunately just a little bit slow in Hydroneer. But we've got, pretend that the durability reader has detected our filter's gone down, it sends a signal, and the hopper sends a wrench out. Our counter now reads a binary value of 1. This is the 1's position, and it now uses this flip-flop to show that 1 is active. If it fires again, the wrench goes off, 1 is turned to 0, and then the 2's position is now on. So 2 shows a value of on, fires again. We've fired 3 times, so we have a 2 and a 1, so that's 3 fires. Now 4 fires, 16. 5 fires, which is a 4 and a 1. 6 fires, 7 fires, 8 fires. So 8 position has been flipped over there. We're down to 12. 9, 10, 11, 12, which is the 8 and the 4. And we're all the way down to 8. 13, 14, 15, 16, which is the last position all the way down here. 17, 18, 19, and 20. And so at this point we would want it to start shutting things down so that it no longer gums up the system with resources getting stuck in broken harvesters and broken smelters. And so we can make sure that the system completely stops itself. And then we can also have it so that once we've repaired it, have the system automatically continue to count all the way down to the point that it resets itself. Boom, 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 boom. So the system resets and then turns itself back on. So I tried creating this initially, which is basically a way of being able to program over here the value that I want to output, and then the value over here is the reset value that I want it to use. And I've got comparison gates, which we're going to be using. This part, everything is going to be kind of the exact same. What's going to be different is up at the top. There is a problem in Hydroneer right now where the logic gates, if you start to stack them, so the equals and the plus, or equals and divide or multiply or anything like that, they don't stack very well because they take the first input that they receive plus and whatever the previous output was. So we may get, 0 plus 1 is equaling to 1 correctly. But right here it shows 0 plus 0 is equaling to 1, and that's incorrect. And you'll get things like this that just don't read correctly and start to create false positives in the system all the time. And so I needed a way of being able to identify in the system why it was causing problems. And I had a bunch of builds that I did over here where I was testing different things. I even went into the Discord to ask in help and looked around in the logic forums, and it looks like this is kind of a known problem. So I've gone ahead, I've got rid of that, and I had to come up with a whole new solution. And so the solution that I came up with was to create this way of using these valves to create a multi-input AND function. So an AND function basically says where every value equals 1, which is our comparison to levers, then it outputs a correct value. But we have a little bit of a delay. There's a 1-second delay because these valves are not immediately opened or immediately closed. And so I've got a series of cables over here that I've gone and taken from the logic shop over in Bridgeport, and then we've got hooks and valves and our gates and all kinds of other stuff that we're going to use to build this. And so we're going to start with my magic wand, because we need an extra button. This button is not something that we would have for the initial input. However, we're going to use that for this input, because this input is for us to be able to test it. But this would be the input from the hopper. So the hopper itself would be what's sending this signal. Now, the way that I built this system initially, I think it's one more out and up than I need. So I'm going to build it one in and one down. And let's try that again. So one in and one down. And I think that lines up. Yeah, so this should be it. And then this is going to be our input. So it's going to do a T, and then we have a straight that's going to come off of this. And this straight is actually connected to a clock. And this clock is used to reset. So it's sending a signal every 2 seconds. 1, 1, 1, like so. And we can actually use a valve, which I believe we got right over here. And that's going to go this way, and like that. And so if we got that closed off, it wouldn't send the signal into the system to automatically start counting everything, but it does prevent it does allow us to be able to automatically start counting if we wanted to. That is how the reset system will actually start to count everything. So now we're going to use a T, which we've got right here, and that's going to go into the button so that when we push the button, we get a signal that comes out of it. So the signal is going to start to snake through the entire system like we did over here, and that snaking process is going to involve a straight line where we have a hook for a flip-flop. And the reason that we do a flip-flop is because we need a signal to be either a 0 or a 1. And then we're going to do a T because we need to be able to fork that signal out in one direction or another. And we're going to repeat this pattern over and over again. So I'm going to actually just kind of copy this a little bit. So there should be 1, 2, 3, 4, 5. And then we'll bring this out and repeat it facing the other direction. So there should be 5 facing the other direction here. And we'll do our straight lines underneath it. Now all of our straight lines are going to have hooks on them, but we're going to alternate the hooks that we do between the flip-flops, which do 0 and 1 signals, and our no 0 signals. And the reason that we do that is because flip-flops will alternate the signals based off of receiving an input, but we don't want them to get a 0 signal and then flip it. So we're going to put our flip-flop here, and then our no 0 here. And then we get it's a 0. Get our flip-flop here. So flip-flop, and then no 0. So flip, no 0, flip, no 0. All the way down. Just go ahead and back that whole thing right up. So flip, no 0, flip, no 0. So this is our last flip. Now we aren't actually sending a signal out past this, so we don't need to add in that last no 0. I've got it here just for the other parts of the system that we would potentially need that for. This pipe actually is going to be completely unnecessary, and you can see that how we've got it in here. With the working example, I put the no 0 just as an example, but we just end up corking that so that it's plugged up. So let's get you put away, and we're going to bring that out of here. So now we need our pipes, our elbows. So our elbows are going to create these zigzag patterns. And again, because we are doing the repeating patterns over and over again, it's actually easier to just do them kind of in chunks. So I'm going to do the top chunk first and then the bottom chunk second. Because now, if I flip this, I'm connecting these. Okay, so this actually would be a fully functional system. However, you wouldn't know if the system actually is giving you any values that you would want to know about or not. And so one of the things that you can do to identify if the values are what you want is you can hook up these lamps. And the lamps can go onto the output from the T's, and it doesn't matter which side you do because again they're going to be before the no 0s, so they're going to output data correctly. So I'd put them on the reset side myself. And the reset side I always choose as the right side, just as consistency. So there's the 1 positions, the 2 positions, the 4 positions, the 8 positions, automatic save. And then the last one is the 16s position down here. So now if I push this button, this is set to 0. And then I push it again, it's now set to 1. And you can see that it's starting to output data from the lines here. And we can actually just open this up and watch it start to filter out the system. But because of the way that Hydroneer logic works, it actually makes more sense to think of the 1 value as an off position. So because 1 can travel all the way through the environment, whereas a 0 cannot, because we're blocking zeros from being able to send. So we want all of the lights to turn on, and that's going to be considered to be the 0 position. So right now we have 16 and a 4, 17, 18, 19. Oh wait, sorry, no, that's 24, 25, 26, 27, 28, 29, 30, 31, and then everything lights up for 0 because there isn't a 32. 32 would be the next segment down here. So this is considered to be 0 at this point. So now we can create our system that properly identifies our values. And so we're going to hook up on both sides of these an elbow that comes out of each one of these T's. And so we'll do the same thing over here. Now each one of these elbows is then going to go into an equals gate. And so the equals gate, what this does is it takes the comparison from one input and the other input, and if they are equal, it outputs a 1. If they are not equal, it outputs a 0. And so we can use that to our advantage here. So we have our equals, and how we use that to our advantage is we have these switches. So these switches, or these levers, I should say, have 2 different modes. They can either be in a 0 state or in a 1 state. And so if we know that our inputs are 0 or 1, and our levers can be in 0 or 1, then our outputs can be in a 0 or 1 as well. So we're going to elbow this upwards. And then we have to put a straight pipe up because we're going to connect these to the logic valves, except for this one, which is, since this is the signal that changes the most frequently, this is going to be the one that we output as our full value. However, because like I mentioned before, the output is not immediate, we need to make sure that that gets delayed. And so we have a 1-second delay that we can hook on right there. So that's going to go there. And then that can send both a 0 and a 1 signal through. And we don't want the zeros, so that's where our extra no zero signal goes in. So that's going to go in this next open spot right here, because our valve is going to go right there. Now, if you wanted to be able to see what the value is, whether it's a 1 or a 0, you'd be able to get a reader that's going to hook onto the side of it. And I didn't actually get the readers here because the valves themselves, they're going to be open or closed. So if we switch this, we know that the value that's being output from this is a 1. The light is on. So this is a 1. That means that this should equal 1, and that means that this is, let's grab my flying helmet. Where's my flying helmet? Way over here. So I added this in. It is currently closed. So if I close that, then this is open. So if I wanted everything to be open, then I would want these levers up. And that would be true for everything. So when I set the entire bar across, which I'm going to do now, the rest of the bar doesn't have any other hooks that are going to go on it. But I will have these valves that get connected. I'm going to make sure that it is in an open state just by flipping the lever a couple of times. And flip that. Make sure that that's in an open state. And there, flip and flip, and check that it's in an open state. Okay, so what that's going to need to do now is that's going to need to come over here and down. Let's move that out of the way. And apparently I am short on several pieces, but that's okay because I've got my magic stick. So that's going to come down this way. And that's going to go all the way over. Okay. So when the system outputs a 1 here, that's going to go through, and all of these are going to be open, and so it's going to go down. But we want to make sure that that flips to a 0 so that that shuts down. So we need our flip relay, which is going to be, or our flip hook, which we can attach it to anywhere on here. So I'm going to actually attach it down here. So that flips it, and then I'm going to attach a relay so that it only fires a signal in that direction, because right here we are actually going to take that single off, or that straight off, and we are going to put a T on, and that T right here is what's going to allow us to be able to put it, or press our reset button. Get that out of the way. And again, we are really short on elbows, so I really miscounted that. So let's get our reset button here. So this, we're going to need a couple of elbows, which are going to come in here, and then it's going to go straight across. I can't push the button or put the button there, so that button is going to have to sit out just a little bit more. Okay. Set you over here because I'm going to need some of those, and one straight across. So my extra button I put right here. So this is my reset button, which we would need on any system that's going to utilize this. And so the reset button, when I push that, is going to send a 1, which opens that up. And now this system is going to automatically count all the way up. Did it automatically close? So it is, seems like it's not pushing the button very much. Why are we not pushing the button? So at some point this is actually sending a close message down. So we're delayed by a second, no zeros, no, and all the way down. It's not catching the signal from that, is it? Well, let's check. We've got a cork, which will attach to the cable, because that is how you stop electricity from flowing, is you cork it. And is properly counting. So that appears to have been it. Because the cable was uncorked, it was sending electricity down, which the cable caught and then turned on. So 2, 1, and that automatically closes with all of the lights off. But we want all of the lights to be on. So do we need to flip all of these switches in order for that to happen? So we push that, and that appears to be it, because it sent the signal and then closed again. So essentially, to identify a specific value, we would do the exact same thing over here. So I don't need to fly anymore. We're going to get rid of that. We've got our gate, or our logic gate. Which we are going to connect up to here and here and 3, 4, and 5. This is where I'm missing out on a lot of the items, or the elbow cables that I needed. I'll have to find where I put my magic wand in a moment. I need to attach the levers. 1, 2, 3, 4, and 5. We need to match a specific number, so I want that one flipped, and I want that one flipped. This cart is now just going to be in my way. There's my wand. I need 1, 2, 3, 4. And then straight cables. And then we'll get these set up where they are creating the bar across the top. We are shy on straight cables too. So I need one more straight cable, one more elbow cable. The straight one's going to go there. The elbow cable, once it's in range, is going to go here. So remember, the elbow comes out of the one that's most active. We are going to delay that by a second, so I need the 1 second delay hook, which doesn't matter which way it faces. The don't send a 0 hook, so that the 0 is not sent, and then we need to start adding in our valves, which are going to be not that direction, should be facing that direction. So that's going to get attached to each one of those. So that's 1, 2, 3, and 4. So now we're going to make sure that everything is correct. So this is, that should be 0, this should be a 1, this should be a 0, and this should be a 1. I believe it is. No, backwards, because again they're backwards. So this is a 0, light on, light off, light on, and light on. So right now we are at 0 for our output. If we push 1 for our output, it's going to be really hard to see if anything happens with this gigantic helmet. Let's get rid of that. Alright, so 2, doesn't look like anything happened back there. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And there was the electricity that fell out the bottom back there. Excellent. So 20 has been hit. The system can now shut off because the hopper has expended everything. I can go and I can fix it, and then I can reset this line so that it puts all of the counts back to green. It lets everything know that the system is back and ready to begin its usage again. Let's get rid of some of these carts. Close, close. And all of the system is back up and running, so let's start counting. 3, 4, 5, 6, 8. So we can just watch it as it counts up all of the numbers. And there's 16, 17, 18, 19, and 20, and then we get an output that goes there. So this sends the system to the control center, lets the control center know that there is now a problem that needs to be resolved. So that is a rather compact binary counting computer system built entirely in base logic that fixes or basically avoids the problem of stacked logic gates that are broken in Hydroneer that you can use inside your builds. Thank you very much for watching. I know this is a longer one, but I appreciate your time. Have a wonderful day.